Right now, sitting inside a payload fairing at Kennedy Space Center is a machine that is about to make the Hubble Space Telescope look almost quaint. Not because Hubble was ever a bad instrument. Hubble is still, after more than 3 decades in orbit, one of the most important scientific instruments humanity has ever built. But the machine sitting on that launch pad right now is designed to do something Hubble was never built to do. Not look deeper, not look sharper, look wider, and look faster at a scale that is genuinely difficult to put into normal words. NASA's own project scientist has said plainly that a single month of this telescope's observations will accomplish what would have taken Hubble an entire century to do. Not a decade, a century. And in a matter of days, it launches. Most people who follow space news know about the James Webb Space Telescope. It gets the headlines, the viral images, the deep field photos that redefine what the early universe looked like. What almost nobody outside the astronomy community has been paying attention to is a second telescope, quietly finished, quietly tested, and now sitting fully assembled and ready to fly, that is going to do something neither Hubble nor Webb was ever designed to do. It is not going after the deepest, faintest, most distant single objects in the universe the way Webb does. It is going after everything else, billions of galaxies, hundreds of millions of stars, potentially tens of thousands of new planets, all mapped out all at once, in a way that no telescope in the history of astronomy has ever attempted before. This is the story of NASA's Nancy Grace Roman Space Telescope, and if you have not heard of it yet, you are about to understand why that is about to change very, very quickly. Stick around, because this channel covers exactly this kind of story before it becomes the headline everyone else copies. And subscribe now so you do not miss what happens when this thing actually turns on. To understand why this telescope matters, you first have to understand who it is named after, because the story behind the name is not just a footnote. It is the entire reason this mission exists at all. Nancy Grace Roman was NASA's first chief of astronomer, a woman who was told early in her career, directly and repeatedly, that women simply did not become scientists. She became one anyway. By the 1960s and 1970s, she was doing something far more consequential than research alone. She was fighting inside Congress, inside NASA's own bureaucracy, for the funding and the political will to build an entirely new kind of instrument, a telescope that would sit above Earth's atmosphere entirely, free from the blurring and interference that had limited every ground-based observatory before it. That telescope became the Hubble Space Telescope, and Roman spent so many years championing it into existence that she earned an informal title inside the agency. People still call her the Mother of Hubble. When NASA needed a name for the mission built to be Hubble's spiritual successor, decades later, there was really only one choice that made sense. Here's the detail that catches almost everyone off guard the first time they hear it, because it sounds almost like a contradiction. The Roman Space Telescope's primary mirror is 2.4 meters across. That is not a typo, and it is not a smaller, cheaper version of anything. It is the exact same size as Hubble's mirror, to the decimal point. If size and sharpness were the only thing that mattered here, Roman would essentially be a modern rebuild of a 30-year-old design. But the entire point of Roman was never to out-resolve Hubble pixel for pixel. It was to solve a completely different limitation, one that had nothing to do with sharpness and everything to do with how much sky a telescope can actually capture in a single exposure. That brings us to the first major leap this telescope represents, and it is the one number that explains almost everything else about why Roman exists. Hubble, for all its extraordinary sharpness, has an extremely narrow field of view. Pointing it at a single patch of sky captures a tiny, tiny sliver of the heavens at a time, which is part of why some of Hubble's most famous images, like its sweeping mosaic of the Andromeda Galaxy, actually had to be stitched together from more than 400 separate observations, painstakingly assembled over time like an enormous jigsaw puzzle. Roman's wide field instrument, built around 18 separate detectors working together to create a single 300 megapixel image, captures a patch of sky at least 100 times larger than Hubble can in one shot. NASA's own engineers have said that same Andromeda mosaic, the one that took Hubble over 400 individual pointings to complete, could be captured by Roman using just 2, not 400, 2. That single comparison tells you almost everything you need to know about the gap between these two instruments. The second major leap, and the one responsible for the number in this video's title, comes from combining that massive field of view with Roman's processing and detector speed. NASA's senior project scientist for the mission, Julie McInerney, has stated directly that Roman will be able to survey the sky somewhere between 100 and 1,500 times faster than Hubble, depending on the specific type of observation involved, with most public NASA materials settling on the figure of roughly 1,000 times faster as the headline number. To put that in terms that actually mean something, McHenry has said that 1 month of observations using Roman would be roughly equivalent to what Hubble could have accomplished in an entire century of continuous operation. Over its planned 5-year primary mission, NASA expects Roman to survey around 50 times more of the sky than Hubble managed to cover across its entire 3-decade career. This is not an incremental upgrade. This is closer to the difference between exploring a single room with a flashlight and turning on the lights for an entire building. The third piece of this story, and the one that connects most directly back to the biggest unanswered questions in modern physics, is what Roman was actually built to investigate once it starts collecting all of that data. At the very top of the list sits one of the strangest, least understood facts about the universe we currently live in. Roughly 100 years ago, astronomers discovered that the universe is expanding. That much has been well established for decades. But in the late 1990s, researchers made a far stranger discovery. That expansion is not slowing down the way gravity alone would predict. It is accelerating, and it has been accelerating for billions of years, pushed along by something scientists still cannot directly detect or explain. An invisible influence they have named, mostly out of necessity: dark energy. Nobody knows what dark energy actually is. Nobody has ever directly measured a particle or a field responsible for it. All astronomers currently have is its gravitational fingerprint written across the large-scale structure of the universe itself, in the way galaxies cluster together and the way light bends as it travels across billions of light years of space. Mapping that fingerprint precisely enough to understand whether dark energy has stayed perfectly constant throughout cosmic history, or whether its strength has actually changed over time, requires measuring the positions, shapes, and light coming from an almost unimaginable number of galaxies spread across an enormous share of the observable sky. That is a job that Hubble, with its narrow field of view, was never equipped to do at the scale required. It is a job that Roman, with a field of view built specifically for wide, rapid, statistically massive surveys, was designed around from its very first blueprint. Dark energy is only half of the story, though, because Roman is being built to attack an equally stubborn mystery sitting on the opposite side of the same cosmic ledger. Dark matter, the invisible material that appears to outweigh all the ordinary matter in the universe combined, based purely on its gravitational effects on galaxies and galaxy clusters, remains just as undetected directly as dark energy does. One of the most powerful tools astronomers have for mapping dark matter is called gravitational lensing, the way massive objects bend and distort the light of more distant galaxies behind them, revealing the invisible mass responsible for that distortion, even though the mass itself emits no light at all. Detecting that subtle bending reliably requires measuring the precise shapes of enormous numbers of distant galaxies across huge swaths of sky, then statistically teasing out the tiny distortions caused by dark matter's gravity. Once again, this is fundamentally a numbers game, one that depends on surveying a massive, representative slice of the universe rather than staring intensely at one small patch of it. Roman's wide field design and its planned survey of roughly 2 billion galaxies over its operational lifetime gives astronomers a dataset large enough to actually attempt this kind of statistical dark matter mapping on a scale that has simply never existed before. Here's a fact about this mission that tends to genuinely surprise people, because it is easy to assume a telescope built for dark energy and dark matter would have little to do with something as comparatively down to earth as finding new planets. The opposite turns out to be true, and it comes down to one of Roman's flagship survey programs called the Galactic Bulge Time Domain Survey. For roughly 440 days spread across its early mission, Roman is scheduled to stare continuously at a crowded region near the center of our own galaxy, taking an image of that same patch of sky roughly every 12 minutes for months at a time. The goal is to catch a specific, rare astronomical event called microlensing, a brief flicker in a background star's brightness caused when an unseen planet, orbiting a completely different star, happens to pass directly between that background star and Roman's detectors, its gravity briefly, acting as a lens and magnifying the light behind it. Catching one of these events requires almost continuous monitoring of an extremely dense field of stars, watching for split-second brightness changes that ground-based telescopes, hampered by Earth's atmosphere, simply cannot reliably detect. Based on how many of these microlensing events astronomers expect this survey to catch, combined with a separate complementary survey looking for more traditional transiting planets, NASA has projected that Roman could ultimately help identify somewhere in the neighborhood of 100,000 new worlds. As of the most recent public tally in the spring of 2026, humanity had confirmed a little over 6,300 exoplanets total, across every survey and instrument combined, over the entire history of exoplanet science. Roman alone, if its projections hold up, could end up finding more planets than every telescope that came before it combined. Let's take a moment to actually picture what that kind of observing power looks like in practice, because the scale here is almost impossible to absorb using ordinary comparisons. Imagine standing in a massive dark auditorium holding a single spotlight tightly focused on one small point on a stage far in the distance. That is roughly what surveying the sky with Hubble has felt like for the last 3 decades. Extraordinary detail, razor-sharp focus, but only ever illuminating one narrow slice of the picture at a time, requiring you to physically move the spotlight over and over hundreds of times just to eventually piece together a single wide scene. Now imagine that same auditorium suddenly floods with light all at once. Every seat, every corner, every detail of the entire stage visible simultaneously, still sharp enough to pick out individual faces in the crowd. That is closer to what a single Roman exposure represents. Julie McInerney has pointed out that displaying just one of Roman's largest survey images at full resolution would require more than 500,000 standard 4K televisions arranged together, an image so enormous it could comfortably wrap around a rock formation the size of Yosemite's El Capitan. Every one of those pixels carries real scientific data, real galaxies, real stars, real light that has been traveling toward Earth for millions or billions of years, finally captured in a single coordinated exposure. There's also a coronagraph instrument riding along on Roman, and it deserves its own mention here, because it represents one of the most technically ambitious pieces of the entire mission. A coronagraph works by physically blocking out the overwhelming glare of a distant star, the way you might cup your hand to block direct sunlight so you can see something faint sitting right next to it. Doing this well enough in space, precisely enough to reveal an actual planet sitting extremely close to its parent star in the sky, at a contrast ratio of roughly 1 part in a billion, has never been successfully demonstrated on this kind of scale before. Roman's coronagraph is designed as a technology demonstration for exactly this capability, aiming to directly image planets around nearby stars, rather than detecting them only indirectly through their gravitational or light curve effects. If it works as designed, it will represent a genuine milestone, a working proof of concept for the kind of instrument that future missions will need if humanity is ever going to directly photograph an Earth-like planet around another star. Now, about the launch itself, because this part of the story is happening right now, not in some distant, unconfirmed future. Roman is scheduled to lift off on August 30th, 2026 from Launch Complex 39A at NASA's Kennedy Space Center in Florida, carried into space aboard a SpaceX Falcon Heavy rocket. The observatory itself weighs roughly 10,500 kilograms, a little over 23,000 pounds, making it a substantial machine even before you consider everything packed into it. After launch, Roman will spend roughly 3 months traveling outward to a gravitationally stable location called Sun-Earth Lagrange Point 2, sitting about 1.5 million kilometers, close to 1 million miles from Earth. That happens to be the exact same general region of space where the James Webb Space Telescope already operates, though the 2 observatories are expected to follow different, carefully separated orbits around that point, rather than sitting anywhere near each other directly. Once Roman arrives, NASA plans roughly 90 days of commissioning, carefully testing and calibrating every instrument before full science operations formally begin, expected to start at the beginning of 2027. From that point, Roman's primary mission is designed to last 5 years, though NASA has noted that if the observatory continues performing well and its fuel and hardware allow it, the mission could realistically continue operating for more than double that length of time, echoing the way Hubble itself, originally designed for a much shorter operational life, ended up running for over 3 decades. Here's something worth sitting with, because it reframes how you should think about everything Roman is about to do. This mission has been roughly 2 decades in development, first proposed under an earlier name back in the 2000s, slowly built, tested, redesigned, and refined. Across years of work by literally hundreds of scientists and engineers, at a total cost of roughly $4.3 billion. Construction on the observatory itself was formally completed on November 25th, 2025. And rather than slipping behind schedule the way many large space missions historically do, Roman ended up launching 9 months ahead of its original planned date. That kind of outcome is genuinely rare in the history of major space telescopes, and it reflects just how much institutional experience NASA has built up over decades of running complex observatories like Hubble, Webb, and now Roman, each one built on lessons learned from the mission that came before it. It is worth being clear about what Roman is not designed to replace, because none of this diminishes what either Hubble or Webb already accomplished, or continue to accomplish. Webb remains the far more sensitive instrument for staring deep into the infrared, capable of resolving individual, extremely faint, extremely distant objects with a level of detail that Roman was never built to match. Hubble, even after more than 3 decades in service, continues to provide exceptionally sharp, focused observations of specific targets that astronomers select in advance, often working directly alongside Roman's own future discoveries, following up on interesting objects that Roman's wide surveys managed to flag. Roman's entire purpose is different from both of them by design. It is not built to look closer at one thing. It is built to look, simultaneously and repeatedly, at practically everything, generating the kind of enormous, statistically rich data sets that the other two. Observatories were simply never designed to produce on their own. Astronomers already expect the three observatories to work directly together, with Roman's wide surveys identifying the most interesting, unusual, or scientifically valuable objects buried among billions of ordinary ones, and then handing that shortlist over to Hubble and Webb for the kind of focused, in-depth follow-up observations that only those instruments can provide. So what happens after Roman actually turns on? Over its first year alone, astronomers expect Roman to generate roughly 20 petabytes of raw scientific data, an amount so large it is difficult to compare to anything in ordinary experience, and that flood of information is expected to keep arriving steadily for years afterward. Somewhere inside all of that data, astronomers expect to find direct evidence pointing toward whether dark energy has remained perfectly constant since the early universe, or whether it has actually shifted in strength over billions of years, a distinction that would fundamentally reshape our understanding of how the universe will ultimately end. Somewhere inside the same flood of data sits the statistical fingerprint of dark matter, mapped across a scale of the universe no previous survey has managed to cover in this much detail, and scattered among the light from roughly 2 billion individual galaxies and potentially 100,000 newly identified planets. There's almost certainly something nobody currently expects to find at all, the kind of unplanned discovery that has defined nearly every major space telescope mission that came before it, from Hubble's accidental confirmation of the accelerating universe to Webb's STILS, unfolding little red dot mystery. If you want to actually understand what NASA's next major telescope is capable of before it becomes the headline everyone else is scrambling to explain after the fact, subscribe to this channel and turn on notifications, because Roman's launch window opens within days of this video going live, and the story does not stop there. Commissioning, first images, first survey results, all of it is coming over the following months, and this channel is going to break down every single milestone with the same accuracy and depth you just watched. NASA already has 3 extraordinary space telescopes in operation right now, and in a matter of days, that number becomes 4, each one built to do something fundamentally different from the others, together giving humanity the widest, deepest, and fastest view of the universe we have ever had access to at the exact same moment in time. Thanks for watching, and I will see you in the next one.